Our last speaker for the afternoon session before the posters is Andrea Bertozzi from UCLA, and she's going to talk about geometric methods in image processing, networks, and machine learning.
So it's a pleasure to be back at Duke again. For those of you who don't know me, I actually spent 8 years here on the faculty before moving to UCLA. So the first thing I want to mention is my brief connection to Ingrid, who is one of many people that sort of indirectly inspired the work that I'm going to talk about. So you may not remember this because it was quite a long time ago. I'm going to skip to the late 1980s. So I actually met Ingrid about 25 years ago, I would say, when I was a PhD student, where I spent fall, winter, and spring in this building. Many of you know where that is. That's Fine Hall in Princeton. But in the summertime, I was in a program at Bell Labs, and one fortuitous day, I ran into Ingrid, who was working at Bell Labs at the time, and we sat down and had lunch together, and she basically taught me in about an hour over lunch kind of all the important aspects of wavelets. And to this day, I still remember the conversation. I don't think I have the notes. But at the time, I thought, this sounds really interesting. It's really far from what I'm working on, so I wanted to kind of put it in the back of my head for possible future use. And indeed, that opportunity came up about, well, I don't know, 7 or 8 years ago when a young PhD student came to me at UCLA. This was Julia Dobrozatskaya. She came from Russia. She had spent her master's degree working on a bunch of problems related to wavelets, and she said that she wanted to work on something in image processing that combined wavelets with some of the UCLA style algorithms, and at the time that was mainly just PDEs. And so we put our heads together and came up with this idea. And so now the idea really stems from the following connection between total variation and L2 problems. So this is called the Ginzburg-Landau functional. This is, of course, many people here know the total variation semi-norm. And at the moment, I'm talking about just Euclidean space differential operators, okay? And so what we can do, at least in the case of partition problems, which is what we're going to be looking at mainly today in my talk, I can actually approximate so this is the binary case here, I can approximate a binary function, I can approximate the total variation norm of a binary function by this functional called the Ginzburg-Landau functional, where epsilon is a small parameter. This is what we call a diffuse interface approximation, and W is a double well potential that has minima at the two values that we're interested in. So this is the idea. Now, of course, if you're studying images, so first of all, if you want to minimize the Ginzburg-Landau functional, you have many very excellent tools at your disposal, not to mention that a lot of people in PDEs on the physical side of applied mathematics have spent many years looking at all sorts of problems related to this, like the L2 gradient flow, which is the Allen-Kahn equation, and the H-1 gradient flow, which is the Kahn-Hilliard equation. Okay, and so when you're designing fast, or you're trying to come up with a fast algorithm for these problems, you notice that they have these stiff operators, the Laplace operator and the biharmonic operator. So one typically appeals to algorithms that address those. So, for example, pseudospectral methods, which involve projecting onto the eigenfunctions of these operators, which are the same. And they take advantage of things like the fast Fourier transform. And so we did some work on this, but of course, as soon as you get into this and you're thinking about image processing, you're basically projecting all the important details of your image onto the Fourier basis. And as we know, that's not necessarily the optimal basis for describing images. And so the idea that we had with Julia, which goes to this slide, was to say, wait a minute, in image processing, you're not constrained to be working with physical equations, right? I mean, you want to use whatever equation makes the most sense for the application. You're not trying to actually simulate material science problems. You're trying to do an imaging application. So we decided we could be a little bit creative and replace these operators here with operators that instead of having the Fourier basis as their eigenfunctions had the wavelet basis, has some kind of wavelet basis as eigenfunctions. And then you're projecting onto wavelets, which makes a lot of sense for imaging. And so that ended up leading to her PhD thesis and a number of papers that came out in the last 5 years. So going forward now, in the last couple of years, having been inspired by these wavelets, I started thinking about problems with much more general problems, not necessarily image processing problems, but large data problems that can be represented by graphs. So for example, this type of a problem where you have many data points that could be very complicated. Here are some examples that are not necessarily from imaging. Well, this is an example like the US Congress, where you have each person in the Congress would have a vector of votes, how they vote, and then you want to try to cluster them based on their voting record rather than some other thing. Also, non-local methods in image processing, where you have a center pixel, it's surrounded by other pixels, and then you construct a feature vector, a very large vector, associated just with that one pixel that comes from looking at all the nearby pixels, and you do that for every single pixel in the image, and then you have a very high-dimensional problem, but with a lot of very useful information. So these are a couple of examples, just simple examples that one can look at with this idea. And so then what we want to do is we want to try to take advantage of all of these wonderful algorithms that come from these PDE ideas to come up with possibly better and faster methods for large graph problems. And I'm mainly talking about problems that we can rewrite as say a min-cut problem or a total variation minimization problem. This is a typo, that should say minimal cut. So unlike the example that Amit talked about, the max cut problem, we're not looking at this one, we're looking at this one, where we're trying to find a minimal cut in a graph where we separate, in this case, 2 clusters, but you could have more than 2, and I'll discuss that later in the talk. And so the point is that the minimal cut problem can be rewritten as a discrete total variation minimization problem where the F functions are assignments of the color, if you will, in this case black and white, but we could do multiple colors. And so I guess the next point that I want to make, probably if there's one takeaway message from my talk, is that TV minimization for graphical problems it's first of all, it's not a linear problem. It really is a nonlinear problem, just like it is in the Euclidean space sense. And so we want to treat it as such, and we want to take advantage of some of these kinds of tools. And so a couple of years ago, I happened to be at China Lake and started talking to Arjuna Flenner, who's spent a lot of time looking at these graph problems. And we discussed the possibility of extending these ideas, the Ginzburg-Landau functional in particular, to graphical problems. So this was the idea here, which is to replace the total variation term in the graph cut problem with the Ginzburg-Landau functional. And here it is in a graphical setting. And notice that the H1 semi-norm is now replaced by this discrete graph inner product, which is effectively the same thing. Here L is a normalized graph Laplacian term. And I still have a diffuse interface parameter here. So this was kind of ad hoc at the beginning. We just said, let's just write this down. And in the simplest case, this is semi-supervised learning. We add a least squares fit to a subset of data, which could be actually a very small subset of the total data. The examples I'll show, it's maybe 3 or 4% of the entire data set. So this was the idea, and at the beginning, I think it was a little bit of a lark just to see what the heck it would do. We discovered it actually worked very well, and not only did it work well, but we were able to leverage a lot of work that's gone on in terms of linear methods for these kinds of graph problems. So basically exploiting a lot of great recent tools, linear algebra tools for these problems. So I talked about this at the meeting 2 years ago here. I mentioned that work. So now, what have we done since then? Well, one thing is a paper with my recent postdoc, Eve Van Gennep. We have some theory proving convergence. So we don't actually, so one of the things that happens when you want to prove convergence is you have to take the epsilon out of the first term. Why? Because it's a discrete problem and we can't, so in the case of the continuum limit, you're basically taking length scales all the way to 0. because it is a continuum limit. For the graph problem, you have a discrete graph. You can only resolve, even if it's a gigantic data set, there's always some finite limit you can go to. And so the epsilon disappears from this term. We still have the 1 over epsilon here, and we can prove in the sense of gamma convergence this Ginzburg-Landau functional to a graph total variation functional, which is very nice. So we now have some theoretical connection. It's not so ad hoc anymore. We now have a theoretical connection between this and the actual graph cut problem that we want to solve. Okay, so another development is the fact that we can actually speed up the minimization of the Ginzburg-Landau functional by about a factor of 5 using a really nice idea that goes back a couple of decades in PDEs, and it's called the MBO scheme, where MBO stands for Merriman, Benson, Osher, who invented this scheme for differential operators. And the idea is if you're trying to minimize something like total variation, what is that connected to? Well, if we think about it in terms of geometry, we're actually trying to do curve shortening or surface minimization in n dimensions. And a typical way to do this is using motion by mean curvature. And it turns out, and this was the idea for their scheme, is that you can approximate motion by mean curvature of an interface by alternating between solving the heat equation for a very short amount of time and then thresholding. So it's a very simple method. So in a recent paper, this is a paper that's going to appear soon in SciEM Imaging Science with 2 of my students. I didn't have a picture of Tiana, so this is just a Katerina Merkuriev and Tiana Kostic. And so here's the idea. Rather than actually minimizing the Ginzburg-Landau functional, we actually take a shortcut. And so it turns out we can't actually solve directly just the heat equation. We actually have to solve the heat equation with a forcing term, but the forcing term just comes from the first variation of whatever this forcing term here is. So in the case of semi-supervised learning, it's just a least squares penalty, which gives us a linear term, very simple. So this is a version of the heat equation. We solve it for a short amount of time, and then we literally just threshold. We set everything to plus or minus 1, or a 0 and 1, depending on the convention you're using, and then you just iterate. And you might think, well, how good is this? How many iterations do you have to do? And in practice, we see that in a lot of sort of common test problems, this often converges in just a few iterations, like 4 for the MNIST data set, which was kind of pleasantly surprising to us. So here's in a sense, the algorithm. What you do is so the expensive part actually is creating a graph from the data, choosing the weight functions. This is going to be expensive for any problem that you're solving. But now here's the kicker, which is that the next step, and you actually don't need to do all of step 1 as long as you can do step 2, which is to calculate the eigenvectors and eigenvalues of the symmetric graph Laplacian. And in many machine learning applications, it's only necessary to calculate a portion of these, often a fraction which is significantly less than 50%, say. So like 10% or something like that. This is and why this is true, I'm not 100% sure. I think this is a very interesting question that I'd like, if people have ideas on why this is true, I'd like to know. But anyway, we just make use of this in practice. Then you initialize U, and then you basically follow this 2-step procedure where step number 1 is carried out by using a method where you project directly onto the eigenfunction. So you're not actually solving the full heat equation. You're doing a sort of a subspace projection version of this, only using the subspace spanned by the eigenvectors that are sort of interest to you. So it's a fraction of the full set. This is a big difference. By the way, this is a huge difference between what we do when we solve PDEs using pseudospectral methods on the FFT. We have to use all the modes, typically, in those calculations. Here, we don't. And then to actually find these eigenvectors and eigenvalues, we can use some very recent stuff from the literature on fast linear algebra routines, like the Nystrom extension or a Rayleigh-Chebyshev procedure, which was invented a couple of years ago by my colleague Chris Anderson at UCLA. So here are a couple of examples. This is, the class, for those of you familiar with the machine learning problems, this is a classical test problem, the 2 moons, that shows why spectral clustering doesn't always work in some of these more complex data sets. So the second eigenvector of the graph Laplacian does not give you the right segmentation, but if you're actually really solving the graph cut problem, which is a total variation minimization problem, this is what you get, and this is what we get using the MBO scheme on that problem. This is actually not a segmentation problem. This is a semi-supervised learning problem where we're taking test data from here and then trying to find similar objects in another image. So we actually have to do comparisons between two different images, and this is using non-local means. So it's a very high-dimensional problem, and for these examples, we use the Nystrom extension to generate the eigenfunctions of the graph Laplacian. Okay, I'm going to skip some of these because I have a lot of slides. In terms of performance time, this is the method I talked about 2 years ago in our paper that came out in MMS last year, and then this is the graph MBO, and it's about a factor of 5 faster, roughly, very roughly speaking, on these test problems. Okay, so now image processing. So non-local means, we can use non-local means to do things like in-painting, and this is an example that comes from my colleague Stan Osher's work from a few years ago. So in-painting with non-local means, if you have a texture, the non-local graphical structure will give you the texture back when you fill in. Local methods won't do that. So we basically get the same results. This is done using the split-Bregman algorithm for total variation minimization on graphs, and this is done using MBO. So the performance is similar. This is in terms of the results. Again, this is Barbara, so this is more of a natural image. We're taking a fraction of the pixels as the ground truth and filling in, and we're getting very similar results to split Bregman. The main difference here is in the time. So if you look at the time it takes for our method to run, it's about, again, around a factor of 5 faster than split Bregman. So we were very happy with this. So I'm going to skip that slide and go on to this slide. So I mentioned early in the talk that you may not want to do a graph cut into two clusters. You might actually want to do a larger number of clusters. In machine learning problems, that's often the case. Here's an example of the MNIST data set, which are handwritten digits. So there are 10 digits, 10 classes. You want to be able to segment into these 10 classes. And it turns out that the MBO scheme and the Ginzburg-Landau functional very easily extend to multi-class. And the idea is, instead of having a single double well or a double well potential where you're looking at the range of the function as being in R and just on the real line, now what we're going to do is embed it in n dimensions and have a potential whose minima live on the vertices of the simplex in n dimensions. And so one can easily construct polynomials for the potential that will have minima, so completely symmetric with respect to the vertices, which is what you want, and then you have minima at those vertices, and so you can construct the Ginzburg-Landau functional this way. And by the way, this has been done in Euclidean space, so this is a natural extension to the graphical case. And again, we have this inner product, the H1 inner product, using the symmetric graph Laplacian rescaled. So MNIST, here's an example with 3 moons. So in the case of the 3 moons, this is semi-supervised learning where we're fixing 5% of the data as ground truth, randomly selecting points, and then having the algorithm find the other 95% of the points for the 3 moons, and it gets like 98.5% correct, which is basically, it's just noise. It's the level of noise that you're not getting correct. You can also classify images very easily. That's sort of an easy case for us to do. And then MNIST. So here's an example with MNIST. So this is the performance on MNIST where we're using, so this is semi-supervised. We use 3.6% of the digits, and we assume the rest are unknown. And then we minimize this Ginzburg-Landau functional with 10 dimensions. And I think quite good classification. Very fast. The algorithm is very fast. It's maybe not quite as good as some of these more classical methods, but these are supervised, not semi-supervised, so it's really a very different problem. The supervised algorithms use quite a lot of data as known for training and then test on a smaller amount of data, whereas we're only using, we don't really have training, we're just assuming ground truth on a very small subset of the data. Okay, so I don't have a lot of time, so I'll just say it's fast. What's the only not fast part about it is constructing the graph and the eigenfunctions, but that's going to be true for anything that uses these kinds of algorithms. We also ran this on some other classical machine learning databases, and I'll just say it did just as well on those. So now I want to get on to the final topic, which is modularity optimization. So this is very recent work that's been submitted a couple months ago with my student Hui Hu, Tamal Ara, and Mason Porter. And modularity optimization comes from the study of social networks. It's an idea that appeared in the physics literature about 10 years ago. And it's basically an optimization. So we can write this as an optimization problem where we're trying to figure out how many natural clusters there are in a social network. And so we have to have a graph and we have to have an adjacency matrix. But the adjacency matrix need not be all zeros and ones. So this could be weights between 0 and 1, which is what we have in the machine learning example. So modularity optimization can immediately be applied to machine learning problems as well as to social network problems. Okay, so I'm not going to go into all of the details of how to define everything, but let me just say that at the end of the day, we're trying to optimize this functional over all possible partitions. So if you have 1,000 members in your set, you could have as many partitions as members in the set, right? Or you could have just 2. So that's part of the problem, is we have to figure out how many natural groups are there. So it's a very computationally complex problem. So this is the beautiful thing about the modularity optimization problem. So using some fairly straightforward manipulations involving just the definition of the graph cut problem and various definitions of these metrics, if we now force ourselves to do just precisely a binary partition, so we restrict to the case of only 2 groupings, it turns out that the modularity optimization problem is equivalent to a total variation minimization problem. So let me go to this slide. So here it is right here. So we have to make some definitions here. There's a number of definitions I have to make, and I don't want to go into a lot of detail on this, but at the end of the day, we can actually rewrite exactly the modularity optimization problem as a TV minimization problem on graphs. So this is the case of 2. So you have to restrict the number of classes to do this. So if I have 2 classes, it turns out to look like this. So you're not just minimizing TV, you're minimizing TV minus this additional term. But this additional term is a very simple term. It's an L2 term with this extra moment term, this M2 moment term. So fairly simple to write down using metrics that are very well known and very easy to work with in terms of minimization procedures. Okay, so you say, well, great, you can do this for 2 classes. Well, suppose it's actually 3 classes or 4 classes or more. Well, if you fix the number of classes to be n, it turns out we can rewrite this again in a very simple way as a TV minimization problem for n classes. So what we end up realizing at the end of the day is that modularity optimization can be solved by minimizing over all the possible numbers of classes these different total variation minimization problems, okay? And so because of that, we can actually use these algorithms that I've mentioned to do this. So here is MBO scheme applied to this. So we started with some data where we knew the answer. So these were sort of simple examples, like the 2 moons. So for 2 moons, you want the modularity optimization to tell you that there are really 2 groups. And so you want to look at the maximum value of modularity over the possible number of groups. And indeed, it does pick 2 as the right one, and this is the segmentation. So that looks pretty good. Here's 3 clouds, and it picks 3. So that's good. I'm going to skip the hard case and go to MNIST. Okay, the hard case, that's the hard case. MNIST, okay. So then we decided to go and look at MNIST. MNIST is interesting in particular because the 4-9 digit segmentation problem is a tough one, since 4 and 9 look a lot alike when you write them by hand. In fact, the spectral clustering method is not going to work on that either. That's a good one to show that spectral methods generally break. So we ran this on MNIST, and let's see, do I have the MNIST? There we go. Here it is. So we ran this on MNIST, the 4-9 classification, and what it does, so here are just two different methods of the MBO method, and what you should see is that on the MNIST data with 13,782 digits, the 4s and the 9s. So first of all, we have two classes, but what you should notice is that the modularity that it picks is quite high, and it's almost exactly the same as the Jen-Louvain algorithm, which is a well-known algorithm for modularity optimization. But the kicker here is how long it takes to run. So the MBO scheme is running in 10 or 20 seconds compared to 110 seconds for Jen-Louvain on this data. And basically this algorithm performs comparatively better and better the larger the data set. So if you're running with only 1,000 nodes on the graph, you won't see a big difference, but with tens of thousands you start to see the difference. So where it gets a little bit in trouble is with very complex data, which is often of interest to the social network people. So let's see, let me go back here. So I'll just mention that there is a benchmark called the LFR benchmark. It's a synthetic benchmark, so you have ground truth and you can construct a graph that's rather complex. So you can have community sizes that follow a power law distribution. So these are rather complex examples. And then there's also a mixing parameter which allows you to mix between different communities. And basically, in a nutshell, I guess the takeaway that we find is when the mixing parameter starts to get high, above a half, the MBO algorithm really starts to degrade with respect to some of the other methods. So where this algorithm really does well is when you have a fairly small number of clusters and fairly well identified groups, although the geometry can be complex. So for example, the two moons is a good example that shows us that you could have rather complex geometry for the segmentation. But as long as you really do have two well-defined clusters, the method will do pretty well. And so I think I'm supposed to finish about now, right? Yeah. Okay, so let me end. I'm not going to show all these slides because this is too much for a half-hour talk. But let me just mention that there's an even newer paper from our group that just went on the archive and is on my website. So 3 of our postdocs at UCLA really put a lot of work into this, developing more theory. I'll just say it's a theory paper that goes over a lot of detail about the theory connecting mean curvature, threshold dynamics, and these phase field ideas on finite graphs. It's like a 50 or 60-page paper. All right, and so the other thing I wanted to mention is an advertisement. We're actually going to be running at ICERM, which is the institute at Brown University, the NSF-funded institute. For the month of February 2014, we're going to be running a cluster group. Cluster group means it's a focused group of people working on the boundary between these kinds of compressed sensing methods and graph machine learning problems, and I'm organizing that. And I believe there is still space for a few more participants. So if people are interested in that program, please come and talk to me. I'd love to talk to you about that. We're very excited about this program at ICERM. So I'm going to stop there.
Questions for Andrea? Yes, then.
I'm sorry, I can't hear you. That's all right, go ahead. Okay, so Stan wants to know why we have to compute the, so you could, he's got a very good point. You could actually do a forward time evolution of the heat operator. So the question is whether you're going to be stuck taking little steps because you don't want to, so here's the thing, you don't want to take a really small time. You don't want to run it for a really small amount of time. There's sort of it's small but not too small. So depending on how small it is, you might want to be computing the heat equation with an implicit method. And when you do that, it makes a lot of sense to be using these kinds of algorithms. And then you can, but let me say something else, which is that, so for example, like in these image processing examples, we don't actually have to, so when we use something like Nystrom extension to compute the eigenfunctions of the graph Laplacian, we don't have to compute all the weights in the matrix. far from that. It's a random method. So you compute a small fraction of the weights, you get an approximation of then you don't even have to compute all the eigenfunctions either. And so at the end of the day, we're actually running an algorithm that's effectively sublinear, doing it this way. But that's in practice. How to prove that we're allowed to do that, I don't know. But in practice, we find that we can often, run something that's effectively sublinear using these ideas. So, excellent question.
So let's thank Andrea.
Okay.